All right, so, and listen, no space talk today, because you know what happens. You saw what happened the last 3 days in a row. You ask me a question, and all I can do is just keep talking about it. I'm not doing that today. I got actual stuff I need to tell you.
I feel like we could just turn this class into like a comic like that. A comic in 5 times. That'd be fun.
That would be far more useful than this random stuff. All right, so what we were talking about on Friday was that if you look at, we're going to go, I'll draw it for a comet. Okay, this is the orbit for a comet, for example. We know it's an ellipse. We know the sun is at one of the focal points. There's nothing at the other focal point. So as my comet goes around, we know that, as we saw in an animation, the velocity here is small. The velocity here is big. Okay? So we know that it speeds up as it goes around, and then slows down, and then slow out there, and then speeds up, and then slows down. And I want to know, okay? I want to know, and this is the big question. If this distance here, and this distance here, we can do this. If at its farthest point, it's 5 times as far away as its nearest point, how many times faster is it here? Right? You see the question? We know it's faster. I want to know how many times faster. So there are 3 or 4 good answers. Okay? We'll call this one VC for V close, and this one VF for V far. All right? So we know that V close is equal to some number times V far. Right? What do you think that number could be? What's a possibility?
Radius.
What's that?
Radius.
Well, I want to know how many times faster is it?
Oh.
Right? How many times faster might it be? What's one possible answer? Yes, sir?
5.
Absolutely, right? It could be. How nice would that be, though? Was that a through the shield high five? That was the best thing I've ever seen. That was amazing. Okay. How nice would it be if that were the actual answer? Right? Could it be 5 times faster? Yeah, it could be. Okay. What's another possible answer that we may have seen something in this class? Yes, sir?
4.
Sure, right? It could be the difference there. I actually like that answer, right? Because the difference here is 4. It could be 4. Excellent. I like that. What's another possible answer? Yeah.
25.
Yes, absolutely. Could be 25. What were you thinking?
I was going to say 16, but I don't know.
No, what? 16 is a reasonable answer, right? What about this one? What about root 5? You see? We have some possible answers here, but we have to come up with a construct. Now, to understand this a little better, let's talk about the force relationship. So I know that when it's far away, the force is small. Remember, the gravitational force is equal to G(m)(m) all over v squared, correct? This means that when the distance is big, the force is small, yes? So this force, this is the force when it's far away. This is the force when it's close. What do I notice about those two things? Right? So the force when it's close is equal to what number times the force when it's far? Well, one of the things you'll notice here is this is a d squared relationship, true? So if it's 5 times as far away, it's not 5 times the force, well, I'm sorry. Because it's 5 times farther away, the force is smaller, right? But it's inverse squared. So in this one, the force when it's close is equal to 25 times the force when it's far. And I know that because what do I notice about that relationship there? It's squared. Okay? So that's why 25 is an absolute possible answer here. Is that cool? Well, here is the coolest thing about planetary motion. I'm going to compare these 2 points again. Okay? I'm going to compare these 2 points again. And what I'm interested in is the torque on our planet by the sun, or on our comet. So, how do you calculate a torque? It's equal to R cross F, right? Which is R times F times the sine of theta, or R, F that are perpendicular, right? Does that seem vaguely familiar? Well, let's look at this moment right here. The R vector is where? That's our R vector. What do you notice about the R vector and the F vector?
Same direction.
They're in the same direction. Actually, that is true. They're actually anti-parallel. They're actually in opposite directions. But that would make the angle 180 degrees and the sine of 180 is 0, correct? So at this moment, there's no torque on it. What about this one over here? Now the R vector is here, but what do you know about the R vector and F vector here? Same thing, right? And so if we compare those 2 points, what do we notice about the net torque? If we compare those 2 points, there's no torque. The net torque is totally 0. And if the net torque is 0, what does that mean for us? That means the angular momentum is totally conserved. That means that the angular momentum, when it's close, is equal to the angular momentum when it's far. Is that cool? All right, so let's write that down. That means the angular momentum when it's close has to be equal to the angular momentum when it's far. How do you calculate angular momentum? This is and what's nice is that you can use a planet as a point particle. So you can do this 2 ways. I'll show you both ways. What's one definition of angular momentum? It's R cross P, correct? Remember that? Angular momentum is R cross P. Does that seem vaguely familiar? So this is R cross mv. So this is rmv sine theta. But here's what's cool about this. If I look at this in the moment, the red arrow is the R, and what do you notice about the V arrow? That's the blue one. Are they perpendicular in that moment? They are, right? So what's the sine of 90? It's 1. So what is the angular momentum then? It's just rmv, correct? Here comes the cool part. I'm going to substitute that in over here. So this is R when it's close times mv when it's close has to be equal to R when it's far, mv when it's far. Is that cool? So far so good? And what I love about this moment is the m's are going to magically disappear, correct? M's are going to disappear. So I'm left with R when it's close, V when it's close is equal to R when it's far, V when it's far. And now, let's come back to this moment. And I'm going to set this up so V close is equal to something times V far. Is that cool? And what do I have? Oh, just kidding. And then so, when you look at this now, what do I have? What's the R far divided by R close? Look up the picture. What is it? What I think is so cool about this is it turns out to be the easy answer, which I love. So if you look at this now, what do we notice? The V close is equal to 5 times the V far. So it turned out that if at your farthest distance you're 5 times as far as you are at your closest distance, you're moving 5 times as fast when you're close as you are far. Which I just love. I love that as an idea. Also, if we go back and look at it, there's another way to calculate angular momentum. Sometimes we can use I omega. So this is like our understanding that if linear momentum is mv, then angular momentum is I omega. If you are a point particle, what is your moment of inertia if you're a point particle?
MR squared.
It's mr squared. And if I'm omega, isn't that v over r? And what are you left with? mr v. So you can see that in this case, they end up as the same expression. It's not a problem whether you use either one here. And this is a question you're going to see on your AP test. You're going to be given a diagram that looks like this, and it's going to show, here's your planet, it's a certain amount of times far away. They're going to say what's the ratio of the forces, and what's the ratio of the speeds. And I think it's cool because the angular momentum is totally conserved. Isn't that awesome? So, when Kepler was looking up at the night sky, he noticed something crazy. He noticed that Mercury, when he watched it from night to night, and even Venus, when he watched it from month to month, they didn't move at a constant speed. I mean, think about it. He had to know that the Earth was going around the sun, and then realize, well, the Earth is going around the sun, and this thing is going around the sun. So in order to figure out the actual speed, I got to take the speed of the Earth and subtract it, and know the angle at which it was at. I mean, think about the math. How cool is that? This is in the 1600s. I mean, come on. But what he realized was that when you look at a, okay, let's say we'll look at a, oh God, all kinds of other, okay? Let's look at a comet again. If it were a circle, the speed would be constant, correct? Which means it would move equidistant in equal time, correct? But what do we notice is happening here? It's faster when it's close and it's slower when it's far away, true? So let's take a given time t. So here's our given time t, and here's our comet. And in our given time t, it moves this far. Is that cool? It's not very far. Why does it not move very far?
It's going slow.
Because it's going slow. Exactamundo. Right? But if we look at its time t some other time over here, let's say we start looking here, right? Is it going to go more distance or less distance? Much more, right? Because it's moving fast. So let's say it goes this distance here. Now, we'll make it a little bit farther. Kepler was like, man, I wonder if there's a relationship here. I wonder if there's like a cool relationship here. And so he's like, what if I just looked at it like this? If I draw a line from the sun to here, and then from the sun to here, right? And I shade this thing in. It's going to take up a certain area, true? Then he was like, but what if this is true? Like, I'm going to look at this. I'm going to take my line here, right? We know that this line sweeps out a little bit of area, true? But what do you notice about this one? This one moves so much farther, but because it's so much closer, what might just be true? How cool would that be? How cool would that be if those areas were the same?
I mean, they probably are.
They totally are. That's Kepler's second law. That any object orbiting another object, a central object, will sweep out equal areas in equal times. And it is the most fascinating idea. Like, to me, the first time I saw it, I was like, that makes so much sense to me. Like, in terms of, like, the world. Like, in terms of my understanding of the universe. That's good. If you were just to do like even just a quick Google search of Kepler's second law, I typed in Kepler's second law animation, this is what we end up with. So it gives you a certain time, and it shows you that now that area, this distance is bigger, but what's true about all those areas? All those areas are the same, which is so interesting. Okay? So this is like a comet, like Halley's Comet, where it's like way out and moving really slow. So even though it moves a farther distance, it's closer, so the areas are equal, which I think is so cool. So when it's closest, it's called the aphelion or aphelion, and when it's well, that's when it's farthest away. When it's closest, it's called perihelion. And I love this because. So, oh man. So a comet is like a icy, dusty snowball flying through space. And when it gets close to the sun's rays will melt it. And as it melts the front, it kicks it off the back. And it pushes it off the back. It's called the solar wind. And so a comet's tail always points away from the sun, not behind the thing. It always points away from the sun. I don't want a subscription.
So do they eventually deteriorate?
Yeah.
Or change pathing?
So they just deteriorate.
Okay.
Because the mass of the thing doesn't matter, but they totally deteriorate. That's why, hundreds and hundreds of years, thousands of years ago, they could see Halley's Comet really, really brightly. I looked for it in 1986, and I was like, I don't see anything. This is a cool little animation here. We're going to see the same thing. But this is for the planet Mercury. Now, what do you notice about the sun here? Is it really in the center? It's not. If we go to Earth, Earth is really a circular orbit. Like super circular orbit. Venus, pretty circular. But look at Mercury. Mercury's pretty offset. It's still an ellipse, but there's one focal point here and one here. And then what about Saturn, pretty circular. Uranus pretty circular, Neptune pretty circular. What about Pluto?
Slight.
Right? And then you go and look at Halley's Comet, now we're seeing something. But again, what's cool is that the area is still the same, which is I love. All right, now for something completely different. So I mentioned to you the other day that the distance, the average distance from the Earth to the Sun, okay, is about 93 million miles, okay? About 93 million miles, but it's not perfect. All right, so get out your Googler, and I want you to find out what is the closest distance to the Earth to the Sun, and what's the farthest distance from the Earth to the Sun. Do that now. It can be in miles. It doesn't, miles is fine for it. It's not a demonstration.
Got it.
All right, give me the closest.
91 million miles.
91,
Yeah.
and the farthest?
94.5.
So the difference between these two, right, is about 3.9.
It's 94.5.
So 3.4.
So it's about 3.5, and it's about 3.5 out of 90, right? So in a percentage, what is that? Maybe 4% different? You see what I'm saying? Like, it's not a huge difference. It is different though, and what that tells you is that there's a closest and there's a farthest. So when we go and we want to look at, for example, F is equal to GMM all over R squared, for example. We're going to use R when it's a circular radius. But this isn't a circle.
Choose D.
So you want to use D, but I want to set this equal to, MV squared all over R also, so I can get the R to cancel and I can figure out the speed, right? You see my problem? So what do I use? Well, we talked about it the other day, and if this is an ellipse, that is the farthest distance.